All right, so now we've reached the part where most of it's going to come through examples now. Just a little bit of talking, but most of we've covered a broad spectrum of content. So most of the rest of the semester will be examples to fill in the gaps here and there in that content. One of those was we had our 4 constructs, right? The selection structures, sequential structures, invocation. We saw all of those. The reiterative structures. That's what we're looking at today. Reiterative structures. Ways to repeat things, to do stuff again. So we're going to look at 3 different types today. And I guess first off, I'm going to do the same example in all 3 types of reiterating things. So let's look at the math we'll need for that example real quick. Okay, so, well, first off, you may have noticed I've gone back to the microphones. I used to use microphones and quit using them, but the sound quality is not quite there, especially if I'm moving back and forth closer and further away from the computer. And it takes twice as long as that to edit if I have a separate sound file and video file. It takes a whole lot longer to edit together, but the sound quality just wasn't that good. And I've noticed on some of those earlier videos, I tend to face the board and talk sometimes. So got to use the microphones. So sorry about the little lags or where it might get off a little. But hopefully it's not that bad. I may get frustrated with it and go back to the other video and just talk louder or something. But for now, back to the microphones. So our examples today, I wanted to do the same thing, all 3 types of reiterative structures we look at. So I was thinking factorial might make a good example. This is a math operation. You may have seen it before. Some of us see it in elementary school when we're first learning our multiplication tables. We learning how to multiply. We see a small sample of factorial. So some of us see it, 3rd or 4th grade, wherever we first learned to multiply. But then it doesn't show back up until Calc 2. So you may have seen that before, you may not have. Our symbol for it is an exclamation point. And basically, factorial means multiply all the numbers leading up to the number in question. So, for example, 5 factorial, that is the number that we get from 5 times 4 times 3 times 2 times 1. So 5 times 4 times 3 times 2 times 1. So all of the numbers leading up to the number multiplied together. So in that case, 5 times 4 is 20, times 3 is 60, times 2 is 120. And obviously times 1 doesn't do anything, except that it doesn't make any sense to stop that pattern at 2. So if we multiply all the numbers together that lead up to 5, we get 120. And that's what a factorial is. And we specifically define 0 factorial to mean 1, in case that shows up. So if we have 0 factorial, instead of just multiply 0, we just go ahead and call that a 1. Then anything else, we just multiply all those numbers going up there. So if you wanted to, you could multiply by 1 more time. I'll kind of show you why in a moment when we get to breaking this down for loops. But the factorial operation, we'll do that math operation for the example in all our reiterative structures. So like 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. So these numbers get really big really quickly, as you can see. And an important part that we'll need for the first example is notice here inside of 7 factorials, we have 5 factorial. So all of this 5 factorial will be found in the factorial of every number bigger than that. That will be important, but for now, just introducing it. So the factorial operation is we take whatever number we're looking at and multiply that by every number leading up to it. Our general way of writing that is some number, the factorial of that number is going to be the number times n minus 1 times n minus 2, and so on, however many we have, all the way until we get back to n minus n, which n minus n would be 0, right? Plus 1. So a really complicated way to write 1, but that's the way we write this formula generically. So the factorial of some number is that number times 1 less than that number times 2 less than that number, and so on. 3 less than that number, 4 less than that number, all the way down until we get to that number minus that number. But then we want to add 1 back because we want to stop when we get to 1. So that's the example we're going to use. That's the math operation we're going to use in all our examples today. So factorials. So I'm going to erase the board and we'll get started in our first example of reiterative structures. Okay, so we're going to use factorials for the examples, and these numbers do get very large very quickly. So when you're testing these, use small numbers, or you'll hit an overflow error. Overflow means it's too big of a number to fit inside an integer, maybe. They get very, very big very quickly. So like 101 isn't that big of a number, right? It's barely reached 3 digits in base 10. 101 base 10, since we've talked about that. It's barely reached 3 digits, so it's not that big of a number. But 101 factorial, it's not equal, is approximately 9.43 times 10 to the 159th power. A huge number. This is about what we would get if we took the number of atoms in the universe and squared it. So these numbers get very, very large very, very quickly. So when testing things with the examples, make sure you stick with small numbers to avoid an overflow error, or throw a couple big numbers in there and see what an overflow error looks like on a computer. So our first one to talk about is what machines do naturally. How do machines work? What aspects of electronics can we take advantage of in order to repeat things? And you've all probably experienced it at some point before. A good standard example is going to be audio feedback. The concept of feedback itself. We're probably familiar with audio feedback. Right? Somebody sings and their voice goes into a microphone, goes down a little wire, hits a speaker, gets amplified, and comes out louder. Well, if things are positioned in a certain way, if everything's set up right, that louder sound is going to go right back in that microphone. Louder sound goes right back in the microphone, down the wire, gets amplified, comes out louder. Goes back in the microphone, gets amplified, comes out louder. And that happens over and over again very quickly, and before long, the room is just filled with annoying audio feedback. And that's what feedback is. The output goes right back to the input. So in our machine, if we take our output and send that to the input, that's what we call feedback. And we're probably familiar with audio feedback from when it's an annoyance, right? When we're sitting in a room and it's suddenly just filled with this loud screeching noise. But it's not always an annoyance. The first two that always pop to my mind would be Jimi Hendrix and Tom Morello. And for both of them, feedback was just another note that their guitar played. Lots and lots of people have done it. Those two just did it exceptionally well. They learned to control the feedback And then it was just another note that their guitar would play. That's what we want to do. That's something we can do, take advantage of with machines. We can do that. We can control the feedback and turn that into just another tool we can use. And when we do that in programming, we call that recursion. And that's controlling feedback, controlling a feedback. Well, I'm saying controlling feedback. I almost said controlling feedback loops, but I don't want to use the word loop because that's something special we're going to talk about in a moment. So controlling feedback to create a reiterative structure. So we'll control the feedback in order to repeat things, to do things over and over again with a little bit of modification so that the problem eventually gets solved when there's very similar steps. Kind of like I pointed out, introduce factorial, 7 factorial. Well, every factorial smaller than that is in 7 factorial. So another way we could think of that would be 7 times 6 factorial. And 6 factorial, we could break that down into 6 factorial is kind of like 6 times 5 factorial. And 5 factorial, we could write that as 5 times 4 factorial. I think you kind of see where that's going. Every smaller factorial is included in the one we're looking at. And that process continues. And that's necessary to do things recursively. So our criteria, in order to do things recursively, it has to reduce to a smaller version of itself. So 1, problem must reduce to a smaller version of itself. So that's why factorials make a good example for this. Because 7 factorial can be reduced to 7 times 6 factorial. And 6 factorial is a smaller version of the original problem. Our other biggest criteria is that the problem must reduce to a base case. It can't do this indefinitely. It has to stop eventually. We have to eventually hit a final point to say we're done. Problem must reduce to a base case. So that's the 2 big ones. I have to do those. And if those 2 criteria are met, there's a couple other things. Those who continue on to computer science classes later will see 2 more items on this list. One of those being the general process by which we call it recursion, which is it has to call itself. Our solution has to refer to itself. Once we develop a solution, we apply the feedback. Our solution has to have the output go back to the input of itself. And that's when it's recursion. So these are our criteria. The problem must reduce to a smaller version of itself. And if it doesn't, it has to be reformulated in such a way that it does. And this is what the machine does naturally. And the problem eventually has to stop. That reduction has to stop somewhere so that we reach a solution. So that's kind of our 2 criteria. Let's look, I'm going to erase the board and let's look at an example of what this is going to look like when we do this in programming.
Okay, so over here in Raptor now and ready to do this. But one thing we haven't seen yet is from this process of recursion, we need feedback. We need our output to go to the input. So in order to do that, we need very well-defined inputs and outputs, and not just asking the user or throwing it up to the console. Because, well, if we're throwing it to the console, we can't send that back to the ask the user box. So it's similar to subcharts. And remember when we talk about subcharts, those are just kind of a breakout thing. They just take a chunk of the one we're in and put it in another spot just to organize it nicely. We need to actually leave and do something else, and that's where procedures come in. So make sure that you're in intermediate mode. So go to mode and select intermediate mode, and then you'll have a button for procedure. So we'll add a procedure, and then we get this little box. What are we going to call it? Well, we're going to call this factorial, because we're solving factorials. And here's where we can introduce our feedback loop, feedback to this. We have very well-defined inputs and outputs being passed back and forth in the background. So for a factorial, well, we really just need to know what number we're taking the factorial of. So I'll call it number, and that will be an input. And then after we solve that, we want to send back the result of that. We want to send back the result. So in this next box, I'm going to uncheck input and send back an output. And I'll call that fact, just an abbreviation of that to avoid using the same word twice. So we're going to pass in the number we want the factorial of, do the processing, and then send back this other thing called fact. So you can see here in the other tab, now our little start bubble has some extra stuff in it. It's taking in a number and returning a number. So first off, I guess we can look at we'll look at calling this in the end. So let's go ahead and fill out the process for making a factorial. So that first criteria listed was to do things recursively, it has to reach a base case, which for factorial will be when we get all the way down to 1. Right? So 5 factorial, we're going to take 5 times 4 times 3 times 2 times 1. And then when we get down to 1, we'll be done. So we'll bring in a selection structure, and we need to see if we're above 1. So that value we passed in, number, is that bigger than 1? Because if it's not bigger than 1, then that means we've reached our base case. So we can go ahead and return our base case. And our return thing, so fact, we want to return our base case of 1. And I mentioned on the board that we have that special definition that if the user gives us a 0, we're going to define 0 factorial as 1. We might want to, we could set things up to spell that out specifically, but here if we hit a 1 or a 0, or any negative numbers are just going to default to that. That's not really what negative numbers are, but we'll just kind of go down to the base case and try to keep the example simple. So when we get all the way down, so if it's not bigger than 1, our output is going to be that number 1, that number we've got down to. But if it's not bigger than 1, well, then we need to take whatever number it is and multiply it by the next smaller factorial. So we'll use the call statement to ask for factorial again. We'll ask for this factorial procedure again. So if we go in here, we want to call factorial, and we can see down here in the predictive, we're taking in a number. So like was written on the board, the next factorial we want to ask, so like 7 factorial was the example on the board. If we're at 7, well, we want to take our 7 and multiply it by 6 factorial. So we're going to ask for number minus 1. So we're going to send one less than whatever number we're looking at right back into this same procedure and see what the next smallest factorial is. And then keep doing that until we get down to the base case. And we're going to get back this thing called factorial. This thing called fact. So we're sending in one less than the number we're looking at, and we're getting back the result of that. And once we have that result, well, then we need to kind of reset it for the next return. So fact will be set to whatever we got back. So this is going to send us something back. I'm going to change the names here. Cancel this one. And I'm going to call this F. Calling that fact is what it was on the inside. So when I get it back, I'm going to put it in a spot called F. Because fact is what's actually being returned. So now we want to set that value that we're actually going to return, which we called fact, to F, which is what we got back here. So if we're not down to our base case, we're going to ask for the factorial of the next smallest number and get back what that is. So then once we get that back, we're going to find the factorial of the number we're looking at. The thing we actually return is that thing we got back multiplied by the number we're looking at. And that is what our method will look like. If we get all the way to our base case, we'll return a 1. If we're not to our base case, we'll ask for the next smallest factorial, and then whatever we get back from that multiplies by the number we're looking at. Let's give this a run and see what happens. So to call this, we'll come over to the main method, and we'll need a call statement to ask for that. I guess first off, we need to know what number the user would like to know the factorial of. So we'll ask the user for that. Which number do you want to know the factorial of? And again, you want to be very explicit in the prompts. Make sure it's very, very clear what the user is supposed to give you and how to input it. Well, floating point numbers don't work so well with factorials. That's a kind of a different thing. So let's make sure and say integer, which and negative numbers are also something different. So let's say positive integer. Which positive integer do you want to know the factorial of? And then whatever they give us, we'll call that user number. We'll store what they give us in a place called user number. Then once we have that, we can ask for the factorial of it. So we'll go to the call statement, and then we'll ask for that procedure we made, which is called factorial, and we're going to send in a number. Well, we're going to send in that number we just asked the user for, and we're going to get back something called, well, it's called fact on the inside, but we can call it something different here. So I'll call it user factorial. So we're sending in this number and getting back this number. So that's the difference between a subchart and a procedure. A procedure is completely separate. We have to send our variables and get them back. We can't just use the same ones over on the other tab, where we actually leave and come back. Well, once we have it, we'll send it out with some nicely labeled output. That way it's not like a magic number that seems to pop up out of nowhere and doesn't have any explanation. We want to make sure it's clear what that is. So we'll say the factorial of plus the number the user gave us, user number, plus is going to be plus well, whatever we got back, user factorial. Did I spell something wrong? No, it's not in the predicted box. So notice that even though we have this variable, we'll put our what we're getting back in this variable called user factorial. It's not showing up in the predicted box. So now when we run this, well, first off, I'm going to turn the speed up and run it quickly so you can see the number come through. So if we run this, which positive integer do you want to know the factorial of? Well, in the lead-in, we used 5 in the example, so we know 5 factorial should be 120. So let's check that. The factorial of 5 is going to be 120. So yeah, that checked out. But let's slow this down and look at what's going on. And notice the watch window is a little bit different now. It labels which one of our charts we're in. It says in the main. So I'm going to slow this down and let's watch what happens as it goes through here. So we ask for the number. I'll enter a slightly bigger one. I'll do 7. That was the other example that kept showing up on the board. So we pass that in. And notice that it's bigger than 1, so it looks like it's not really changing here. But if we look over at the watch window, we have this stack. We're stacking up a whole bunch of these factorials. Oh, once we get down to 1, then we start passing things back. And it comes right back to where it was, and then just finishes out that piece of the stack. And here you can see those numbers get very big very quick. Going from 5 to 7, we went from 120 to 5,040. So I'm going to come over here and make some marks on here. So what's going on each time, if I turn on the ink, what color am I? Green, that might not show up so well. Undo that. Let's change that to red ink. That'll probably show up. Or we can use a couple colors. So once our main calls this the first time, we come in and like with the 7. It's bigger than 1, so we're going to go this way. And then factorial, first thing we're going to do is call factorial minus 1. So we're going to subtract 1, and then we're going to go right back into the factorial method with 1 less than what we did the first time, which was still bigger than 1. So again, we come through here, and again, first thing we hit is the factorial method, and we're going to call 1 less. So then, once again, we come back, call the next factorial, and we'll keep doing that with our number being 1 less each time. And eventually, we'll hit the base case. We'll get down all the way down to 1. And at that point, we'll take this branch. Oh, factorial, it's equal to 1. So we're going to set our output variable to 1. And then come on down to the end block. And once we hit the end block, well, it goes back to where it was. So then it'll jump to the most previous call statement and finish running through here. At that point, it reassigns what fact is again, hits the end, and goes back to the most recent call statement. Goes through there again, reassigns what fact is, hits the end, and goes back through. And that's going to keep repeating until we get all the way back to whatever our original number was. And at that point, it'll jump back over to the main. So let me clear that ink off there. I thought I had a clear button somewhere, but I can't remember where it's at. There we go. So let's run that again and watch it go through there again. So we run it. And let's check 12, a bigger number. Jumps in there. Well, 12 is bigger than 1, so it calls factorial again. And we end up with this stack of these calls, of these call functions. We keep calling factorial over and over and over again. And we get a bigger and bigger and bigger stack. And once we finally get to a result that we know that we're returning an output from, so fact1, then we just keep passing that back. And notice now that f variable is filled in. So then we can multiply that by the number that was passed in and keep going back to that spot we left the method from originally and end up with a very large number. So that's how recursion works. That one was probably very confusing, right? So really just introducing it here. Let's go back over to the board and talk some more about that. Recursion is what machines do naturally. So it can be faster. You may often hear in reference material recursion is going to be faster, but if you think about that, you'll quickly realize that that is kind of dependent on how nicely your code's written. Right? If you write really sloppy code that is terribly inefficient, that's going to slow recursion down as well. And then you have the nicely built things by really, really good programmers that wrote the programming language running pretty quickly. So the faster, you'll see in reference material that it's faster, but remember there's details there. Right? If you write really sloppy code, it's still good. It's going to go the speed of the sloppy code that you wrote. But it can be a lot faster because this is what the machine does naturally. But there's kind of an issue, right? That was probably a little complicated. And this example fell naturally into our criteria. Every pass of a factorial is, I can turn that off. Every pass of a factorial is a smaller example of a factorial. So this naturally met our criteria. But not every problem is going to.
So that's how we use feedback to create a reiterative structure. That is what machines do. That's the natural thing for machines. So in every single programming language, every way we have to give a machine instructions, we can use recursion. And then we have these two criteria. And for those that continue on to maybe a 4-year computer science degree, you'll see two more things on this list which are relate to applying that. We did see them there. I just left them off the list because we're introducing it here. This is just an introduction because recursion can be very complicated. So we look at it as small steps along the way and hopefully make sense of it. But that's what we always have with the machine. Feedback. We can always send our output to the input. And our example here was specifically chosen to meet these two criteria. So that's how complicated it is with an example that naturally does that. If we have a problem that doesn't do that on its own, we have to reformulate that. We have to reorganize our algorithm until we find a way to state that problem that it does fit this criteria in order to use recursion. Which makes it a little, can be very complicated at times. That can be very difficult. So to get around that, people developing programming languages invented what are called loops, which is basically a syntax that we use in our programming language that rather than revolving off the base case and repeatedly calling itself, the whole feedback thing, there's a syntax we can use where the stuff we looked at last week, the Boolean algebra conditions, and just have true or false questions, or answers to true or false questions, we can use that to determine how many times it's going to reiterate through the structure. So our next two examples are versions of that. So let's get into the loops, which are a whole lot easier to use. And way more programming languages have loops than not. But this is the one we always have. So if you're working in a language that does not have loops, this is what you have to do.